Hi, welcome to this webinar on the Hopsworks Feature Store and how to use the Hopsworks Feature Store from the Databricks platform. My name is Jim Dowling, and I'm going to be the host today. And I am the CEO of a company called Logical Clocks. So let's have a look at the context in which the Feature Store exists. If we look at the last few years, many teams have built what we call an analytics pipeline. You can see at the top here in the diagram. In the top left, we have many sources of data. We have raw data, we have tables, we have event queues, and then we have data pipelines, which will take that data, clean it up, and organize it so that it can be used from a data lake or a data warehouse by BI platforms, business intelligence platforms like Tableau or Power BI. Now, this has helped companies understand historical patterns in their data, maybe how has purchasing and how has sales gone in recent times, and then hopefully they'll be able to understand those patterns and be able to take business decisions based on the information they've gleaned from those patterns. What AI is about for the enterprise primarily is about building predictive models. So being able to build models that help them predict things that they don't know today, and the data they need to build those models is already there. It's in the data lakes, it's in the data warehouses, and the challenge is how to get that data out of those data lakes and data warehouses and into the hands of data scientists who can train models, but also into the operational applications that will use online models, so models in real time, to make predictions. So things like fraud, being able to predict customer behavior, to be able to help drive recommendations and sales. So what we're going to talk about primarily in this webinar is the bottom orange area. We have feature pipelines, and they're code similar to the data pipelines that will take data from our existing data sources, transform that data into features. So features are the units of data that we use to train models. It's numerical data that we feed directly into a model, whether it's scikit-learn or TensorFlow or PyTorch. And that data we're going to cache in something called the feature store. So the feature store will be like a data warehouse. That the way the data warehouse works for BI platforms, the feature store will work for data scientists, but also for online models. So they can go to the feature store to get their features to make predictions in the case of applications. But in the case of data scientists, they get their features because they want to train new models, but also batch applications should be able to go to the feature store and do analytical model scoring. So this part, the data part, is, as you can see in the quote in the bottom left-hand corner, this is one of the main challenges that you'll find in building out AI infrastructure and platform support in the enterprise. So the feature store lies somewhere in the middle between data science and data engineering. On the left-hand side, we can see that data engineering deals with our data warehouses, the schemas for them, the types of the data that we put in there. We use schemas to ensure data quality. But data scientists on the right-hand side, they'll typically train models with NumPy arrays, with numerical features, categorical features. This data will primarily be numerical data in 32-bit floating point number format. And we need to get the data from where it resides currently on the left-hand side into the data science world on the right side. And that's the challenge that the feature store addresses. So let's have a look at how we do that. We do that with a process called feature engineering. It's about transforming the data. So here we can see a table with two columns, an ID, and then an array of features as the second column. Now we can see if we look at the array of features on the very last row, we have a number of values. And there's quite a spread between the numbers, between 3 to 10. And a data scientist might say, well, I would prefer to have not as big a spread between the numbers because that induces numerical instability when I'm training the models. I'd like the models to train faster and converge better. So what I'm going to do is I'm going to normalize these values in the arrays. That means I'm going to squash them into a range between either 0.5 and minus 0.5 or 1.0 and 0. So L1 normalization is a type of normalization you can apply to in this case, to a data frame, a column in a data frame. And you can do that in Spark. So if you're working with Databricks and you're writing code in PySpark, you might write code that looks like the following. We have a data frame called scale_df. We read up that data frame from a file, a Parquet file somewhere. And then we have a normalizer that we set the input column to be the features, and we're going to compute the normalized version of these features in an output column called L1_norm. And then we call the transform method on this normalizer, and it will actually then create a new column in the scale_df data frame. And then we can proceed to drop the original features column. Now we have some transformed data. We have the original data that came in our features, and it's now normalized features ready to be used to be trained by models. So normalizing or transforming data, zero meaning data, we can do this often within a single table. So we have one table here, and this can be made to scale out pretty easily. Another common type of feature engineering is to compute what we call aggregations over the data. So on the left-hand side, you can see we have some raw data for hotel bookings. And this is what you would typically find in an operational database. We might have information about what rooms were booked on what dates. So we can see we have a booking row includes when the booking started, the date that you arrived, the date you left the room, and then the room number. Now, that information, while useful, is not as useful as a feature called load factor that we can see on the right-hand side. So load factor contains a more condensed set of information about the level of load or the relative number of bookings to empty rooms in a given room in a given period of time. So the period of time here is the month. We have a load factor for the month of May 2005. And the load factor is 90%. Now, you might compute load factors for months, for weeks, for seasons, for years, and these features then become reusable. You can use this feature, the load factor feature, to maybe predict potential future income in a room in a hotel. You could use it to predict periods when you might want to do renovation, or you could use it to predict periods when you should have sales and marketing and how to adjust the price level so that you maximize revenue on that room. So the aggregations and the transformations we looked at, you can do many of these in SQL. So if your data is in a data warehouse or a data lake and you can run SQL against it, you can probably do a lot of good transformations. You can do some aggregations and even some validation of the data. The data, for example, the load factors between 0 and 1, for example. You don't want the load factor outside that range. And obviously our schema doesn't help there. The schema will just say it's a valid floating point number. So what we find most shops are doing nowadays is they're actually using Python instead of SQL to do feature engineering. So Python is a very versatile language for reading data from many different sources. So from backend databases, of course, but also from file systems, distributed file systems, object stores, event queues, Kafka. So Python supports reading data from many of these sources. It's not particularly efficient, so some shops will use Scala or Java to build more efficient feature engineering pipelines, but it's very versatile and there's a lot of competence out there. So a lot of shops do still build Python feature engineering code, and the two main parts of this feature engineering process are, one, we want to transform the raw data on the left-hand side into the features. But second thing we also want to do is we want to validate the data, because the schema is not enough. The schema will not tell us if our load factor is a valid load factor. If an invalid load factor, let's say 100 or 200 appears in a training pipeline, it can really skew predictions, and it's very hard to identify and debug that type of problem. So we want to anticipate any potential problems in data and identify those problems early through data validation. Now, our particular feature store, the Hopsworks Feature Store, it's built around three main concepts. We have the concept of features, we have groups of features that we compute together, and then we have training and test data sets that we create by joining features together. That means reusing features. I'm going to start with the features themselves, and these are two examples of groups of features. One is very well known, it's the Titanic passenger list data set. In this particular case, in the Titanic passenger list data set, it's a well-known data set where you train models to predict if a passenger survives on the Titanic or not. I'm just going to pull up a pen here so that I can ring some of these things. So there we go. Let's move that around here beside me. And I'm going to move it back. Okay, so in the case of the Titanic passenger list, what we want to do is we want to predict if a passenger has survived or not. And we can imagine that this particular group of features were uploaded together because it was a single data set. But in a production system, you might have data coming from different data warehouses, different tables in those data warehouses. Excuse me. From different data lakes and from different event queues, for example. So feature groups are natural abstraction where you write pipelines that come from these many different locations. You say, well, the backend data source is updated once an hour, so I'm going to update the feature store feature group once per hour, or this particular feature group's updated once a day, we'll update it once a day. Now, in this example that I have here, the passenger bank account refers to the amount of money that the passengers on the Titanic had in their bank accounts when the ship sunk. So a data scientist might come here and say, well, hang on, I'd like to create a new data set that adds this bank balance to the original Titanic passenger list data set, because now I have an extra feature that might help me predict better if this passenger has survived or not on the Titanic. So the data scientist joins the features together that they need, that he or she needs to train their model. And then they decide, okay, what am I going to do? Am I going to work with this training test data set as a data frame? And our feature store will give it back to you as a pandas or a PySpark data frame. Or you can basically say, well, I'd like this as files. So the files you might want to have are TF record if it's TensorFlow, NumPy for PyTorch, CSV for scikit-learn, Petastorm or Parquet if it's SparkML. And you might then decide to store this in a bucket in S3 so that your data gets output to a bucket. You can do this if you have very large volumes of data. This is maybe something that you want to do during the night before you arrive at work, and it'll create your trained data set from the latest data that's been arriving into the feature store. And then when you arrive at work, your trained data is ready to go. You don't have to wait to backfill those training data pipelines. We version the features, the feature groups, and these training test data sets that you're able to reproduce trained data sets at a given time. And in fact, if you back your feature group by Hoodie, which is a framework developed, it's an Apache framework developed primarily by Uber, but we also support, similar to Databricks Delta, will support commits for every time you do an update on a feature group. So we call that an upsert. Either it's updating the feature group or it's inserting new values. And we'll get a commit ID associated with that. And with this, we'll be able to use time travel on feature groups. We're able to say, okay, give me the feature group as it was on the 1st of January 2019. So give you the state of the feature group at that moment in time. So these feature groups are ingested at different rates or cadences. Ones that are updated very frequently, feature groups that are updated very frequently, we call them low latency features. And feature groups that are updated infrequently, we call them high latency features. So low latency features might be, for example, if you have a website and you're making a prediction of whether to give a loan or not. So what you might do is you might ask the user to enter some information. You might also have a lot of historical information about users and the economy and so on. But many of the features the users will enter on the website. So you want to convert whatever the user has entered in the website into features within a second or two so that the user has a nice interaction with the website. You also have many features that, for example, user clicks, and they get updated every 10 seconds or so, or every 5 seconds or 20 seconds. And you might have a streaming app that is collecting from example, Kafka. It might collect all of the time a user clicks on something it'll count those, and then those counts and windows of those counts. So maybe the counts might be the last minute, the last hour, the last 30 seconds. They'll get updated in our feature store. You might also have operational databases that push out the changes to those operational databases every 30 seconds. So with the CDC, a change data capture API, and you can have a streaming app that processes that data. You may also have a pandas application that takes changes to your data warehouses, maybe once an hour. If a new partition is written to your data warehouse once an hour, but you can have a featured pipeline that will take those changes and push them again to the feature store. And then finally, you might have data in your data lake that gets updated less frequently, and that gets featureized and pushed to the feature store when it's changed. So these feature pipelines, all of them will run at different cadences. Some will need to be streaming apps, some will be batch apps that are scheduled once an hour, once a day. But what they're going to do is update the feature store with the features so that the online applications that we have here are able to get any historical features they need. So if the user enters their insurance, their application for insurance, and they enter some features here, we might get, for example, the social security ID of the user. And with that, we can look up a lot of features, historical features about that user. So maybe we have credit histories, credit scores, and so on. The data scientists will use the feature store to create training and test data sets, and batch applications will use the feature store to score models, so to do analytical models. So it's going to take data that's or features in the feature store, and maybe it might do something like predict which users to target in a given marketing campaign. So maybe the features related to users are in the feature store. Now, one of the challenges you have here is that the online applications should have very low latency access to these features. So if it's going to retrieve features to make predictions, it should do it in double-digit millisecond latency at worst. The training requirement and the batch applications, they might require large amounts of data, terabytes or even petabytes of data. And the challenge we have is that we don't know any existing database that has this multi-petabyte scalability and low latency access. So what we at Logical Clocks have done with the Hopsworks Feature Store, but also all other known implementations of feature stores that we've encountered, have dual database systems. They have an online feature store and they have an offline feature store. So the online feature store in our case is an in-memory distributed database called MDB or MySQL cluster. And the offline feature store is Apache Hive. And in our case, Apache Hive will store its data on our file system, HopsFS, which ultimately, if you're on AWS, it will store it in buckets in S3. So your data will be stored in buckets in S3, so you can scale out storage independent of the feature store itself. Now, the challenge that having an online and an offline feature store introduces, we can see here visually, we have this pipeline going in here, and then we have this dotted line showing the features going into the online and into the offline feature store. Now, the problem here is that if you're a developer and you're developing some feature pipelines, do you need to now know how you're going to synchronize the data between the online and offline feature stores and handle all potential edge cases if there are failures or partial failures? And that's where the Hopsworks Feature Store should help you out, because what we do is we introduce an abstraction called a data frame API. So all of the features that you're going to compute and you're going to add to the feature store and materialize in the feature store, they're going to be pushed in as data frames. So whether it's a Pandas application or a PySpark or a Scala Spark or a Spark streaming app, we can push the changes, the features that you've computed into the feature store as data frames. And the complexity of dealing whether a given feature group is online or offline is handled by the platform. The platform will basically do the heavy lifting of ensuring the consistency of features in both the online and offline feature stores. So the end result here is that we simplify the ingestion of features into this online offline feature store by providing this general purpose data frame API. So let's have a look at the code. So what will your code look like in Hopsworks when you want to compute features and when you want to add them to the feature store? So we said already that features come in as feature groups. So what we're going to do ultimately is we're going to take a data frame and add it to the feature store. And we're going to give that feature group a name. And then we're going to say whether we're going to add it to both the online and offline or just the offline feature store. So in this case, we're adding it also to the offline feature store, the online feature store. So if we look at this code and examine it, firstly, we have a Hops library and we're importing the feature store as an object called FS, it's a module. And then we'll import pandas. The next thing we'll do is going to read up a data frame, and we're going to read up some delta data in an S3 bucket. So we have a delta table called telco data. And this data is available on a GitHub repo. I'll point it out later on. And we read it up as a Spark data frame. So it's a PySpark data frame called DF. And then we're going to convert that data frame to pandas. Now we're converting it to pandas in this case because pandas code for feature engineering is very nice and very easy. Now, if your data volumes are large, you might want to keep using PySpark to do your feature engineering. Now, there is a lot in the example notebook that we'll cover later. There is a lot of feature engineering in here. We skip it or elide it in this example. But what you're typically doing are the transformations and aggregations that we introduced earlier on that data frame. And when you're happy with it, you can then go ahead and register this feature group with the feature store. If this is a pipeline that's updating an existing feature store, you can instead of calling create feature group, you want to call upsert on the feature group. So I mentioned already that these feature engineering pipelines will do aggregations and transformations. But the other thing that they'll typically want to do is validate your data. And I mentioned already that if you have invalid values that appear in your data, you do have some recourse if you're using Hoodie, because you can always roll back your data and say, well, this feature group version 12, there was some bad data got ingested here. So what we can do is we can roll back to feature group version 11. But you still have to identify that that was the commit where the bad data came in. So data validation is a general purpose concept that we want to apply to feature engineering pipelines. So we have library support for that. I'll cover in a second. So just to summarize, feature engineering involves taking the data from our existing data sources, transforming that data into features and computing aggregates on those features, and then validating the data to make sure it's correct before we add it to the feature store. So how do we do feature engineering? If we're assuming Python is the lingua franca for feature engineering, and you're doing single host, small amounts of data, pandas is obviously a workhorse in this environment. Feature tools is also a good library. If you need to handle larger volumes of data, you're going to have to go distributed. So Dask is one framework that's used a bit, but we're going to talk primarily about PySpark today. So PySpark is the version of Spark that's implemented in Python and it runs on Databricks and also on the Hopsworks platform. Now, other popular frameworks for distributed feature engineering are Spark, Scala, Java, Flink, primarily Java, and then Beam, which supports both Java and Python, but runs primarily on Google Cloud Platform infrastructure with the Dataflow runner. So data validation is a newer area, and you won't find as many frameworks. So there's a really nice framework for single host Python applications called Great Expectations. You can use it in PySpark, but it's not natively designed to work with the Python or PySpark data frames as of today, as far as I'm aware. You can work with TensorFlow Extended on Beam, and it has a data validation library, which is quite nice. And there's a gap here, actually. The gap here is that for PySpark, we don't have any really good native data validation frameworks today. We do have DQ, which runs on Scala on top of Spark. And in fact, our platform provides UI-driven support to define data validation jobs using DQ. So from your UI, you can take a data frame or a feature group, and you can define predicates on that feature group. So you might say, for example, the number of rows that will be ingested will be within this range. We'll have at least 100 rows and not more than 1 million. You can then define predicates for individual feature values, so the range of the feature values. So the load factor will be greater than or equal to 0 and less than 1.0. And you might have global predicates that you can define over a individual feature. So for example, all the values of this feature should be unique, or they should be 50% of them should be distinct. So there's the DG framework is quite rich, and you can go through it, and also Great Expectations. They provide many of these predicates that can be written in very human readable form. So we want to take in these features from all these different data sources into the feature store, and we want to use those features. And we want to use those features in online applications, in batch applications, and for training and test data sets that data scientists will work with. So data scientists, they'll typically want to use the feature store to create training test data sets. So one way they can do it from within their Databricks cluster, so this is the external Spark cluster here, is they can use our APIs to get back a data frame that joins together features in the feature store. And that data frame can be materialized to a bucket, stored in a bucket in S3 in a given file format. To do this, what you'll need to do in the Hopsworks platform is, firstly, you'll need to create an S3 bucket and a connector for that. So you'll need your S3 bucket on AWS. In Hopsworks, you can just define that, give that bucket a name so that it can be used inside your programs. And here we can see how we can use a connector to an S3 bucket. We have the same code as before, where we join these features together, and the query planner in Hopsworks will find the common join key for these features in the different, there's 2 feature groups involved here. And it will give us back a data frame with all of these features. And that's the data frame sample data. So to create the training data set, we call fs.create_training_dataset, pass in the data frame, the name of our training data set, the file format that we want. Optionally, you can put in the version number. You can also call it get latest version +1. And then if we're storing it to a bucket in S3, we point it to the connector that we defined in the Hopsworks platform. So we said the sink is SageMaker Gym, and that's the name of the bucket I use for a different webinar. And then it will materialize that data frame in TF record to that particular bucket. So Hopsworks is available as a SaaS platform, a managed platform on AWS, and it's available at hopsworks.ai, www.hopsworks.ai. It's currently available as free beta, so up until September, you can go ahead and use it. There will be no charge. And this is how it works and integrates into the security environment in AWS. So in AWS, you have your Hopsworks cluster here, and the Hopsworks cluster, when it's running, you can run jobs on Hopsworks as well, not just on Databricks, but they'll run as an IAM role. So the cluster can be given an IAM profile when you define it, and then the Hopsworks cluster and jobs run on it can interact with any IAM-enabled services on AWS. Now, for users who are using the cluster, they can access the cluster by logging in. So if you use Hopsworks AI, either you'll be asked to define LDAP, an Active Directory or LDAP connector and configuration, so you can hook it up to your LDAP or AD server, and then the users who are registered there can use this cluster that you've defined, or by default, we'll just give you credentials, and you can then log in with those credentials. For Hopsworks Enterprise version, we also support OAuth 2. It's currently not available in the managed platform, but will be soon. And then finally, if you're using Databricks over here and you want to access the feature store, and we saw some example code earlier, you'll need to connect. So there's a little bit of code that's run like the fs.connect. And the way that code will work is that Databricks Notebook will be run as an IAM role. So when you start your Databricks Notebook, you have an IAM role. We'll write that down here. IAM role. And that IAM role, what it will do is it can be used to talk to the AWS Secrets Management Service. So there's this Managed Secret Service in AWS, and we'll register this API key here, and we'll basically say that this IAM role is allowed to read that API key. So when you call connect from the Databricks Notebook, it will go to the Secrets Manager, Managed Secret Service in AWS with your IAM role and say, please, can I get the Hopsworks API key? And then this will happen transparently. It will get the API key, and from then you can now access the Hopsworks platform. So no keys are stored anywhere in notebooks, of course. Now, how does this fit together? We've talked primarily about feature engineering and the feature store, and you can do that on Databricks, you can do it on our platform. But once you have your features available, data scientists will select those features to train models, and they may or may not decide to materialize those features as train test data or just work as data frames. And then we have the iterative process of designing models. So designing model architectures, finding good hyperparameters, validating your models, scoring them. And when you're happy with your models, you can save them in a model repository or model registry. For example, MLflow in Databricks is a model registry. Hopsworks also has a model registry. From your model registry, any batch applications, so Spark applications, can go ahead and use the models so you can build analytical ML apps very easily from here. But also, when you have a model that you want to make available to online applications, because it's going to be used as an operational model, you then want to deploy it to serving infrastructure. So SageMaker is a well-known model serving infrastructure available on AWS. Databricks, I think a week ago or so, introduced their own model serving infrastructure. Hopsworks also has model infrastructure, model serving infrastructure built in, where it will use an external Kubernetes cluster, such as EKS on AWS. But the role of the feature store when you're serving models is quite important, actually. So it fulfills two main roles. The first one is that your online application, that maybe it's using features that the user entered from the website, but it gets in a user identity. So maybe we'll have the social security identity for the user. And with that ID, we can go to the online feature store and say, give me the historical and contextual features related to this individual. So information such as how many times has this user clicked on this website in the last 6 months? It's not available in the online app, but the feature store has it. Give me the credit score of this user. Again, the online app shouldn't necessarily manage this data, but the feature store has it. So the online application will use these identities and these entity keys, as we call them, to go to the online feature store and build feature vectors. The full feature vector that was used to train the model using all of the features. So maybe only 10 or 20 are available in the online app. But when I train the model, I use 250. And that's a case we had at one customer. So the online feature store builds the full feature vector and gives it back at very low latency to the online app. We can then pass the feature vector to the model serving server to get a prediction. This can also be done within the model serving infrastructure itself. It's up to you as to where that logic resides. Now, how do we integrate Hopsworks with Databricks? So this is more operations. If I want to deploy Hopsworks AI, I want to deploy a Hopsworks cluster on Amazon, how do I get it to connect to Databricks? The easiest way to get started is to deploy your Hopsworks cluster in the same VPC and the same subnet as your existing Databricks cluster. So we'll see when we start Hopsworks AI that you can select the Databricks VPC if you're in the same region, and then you'll want to select the same subnetwork as your Spark cluster is started on. This way, all we'll need to do is open some ports on the Hopsworks Feature Store, and we can do that with 2 or 3 clicks. and then Spark on Databricks can talk to our feature store. So an alternative, if that is not considered an acceptable way of deploying Hopsworks because of IT policy, would be to use what's called VPC peering. So you can deploy Hopsworks in its own VPC, and then you can set up VPC peering between the Hopsworks VPC and the Databricks VPC. And you can contact us for information on how to do that. So this is the checklist for how to deploy Hopsworks within the same VPC and subnet as Databricks to get started. The first thing you'll need to do is to create a Hopsworks cluster. And you'll need to do that, you'll need to create an account. And once you've created an account, you'll need to set up what's called a cross-account role on AWS. So in your AWS account, you'll need to create this cross-account role. We'll give you instructions. It's basically 3 steps. It's only 3 steps. It's very similar to Databricks. And once you've created the cross-account role, maybe you need to talk to your IT to do that. And we have another way of creating a cross-account role with very limited privileges if your IT are sensitive about the privileges given to Hopsworks.ai. But once you've created that cross-account role, you can now create your Hopsworks cluster in the same VPC as Databricks and the same subnet. Once you've done that, you'll just need to open the ports. It's a couple of clicks. And then finally, we'll need to create this API key in Hopsworks and make it available in Databricks. So we add that to the secrets management service in AWS, and then we make it readable by the IAM role used by Databricks. So all the details for how to do this are available at this URL below. And I'm not going to go through all of that today, but we'll see some of the steps that we need to go through. Now, Hopsworks has a bit more than just the feature store. It supports training of models with GPUs, and we also support multi-worker training, so training with tens or hundreds of GPUs. We also support hyperparameter tuning asynchronously, which is quite unique on PySpark. And we also support parallel ablation studies, again, using PySpark. And this is a framework called Maggie. There are a couple of talks at the Spark AI Summit you can follow to see our work in these areas. And the platform itself also supports what we call project-based multi-tenancy. So you can have more than one feature store inside a single Hopsworks cluster. You can have a dev, prod, and a staging cluster, or you might even have another sensitive feature store that you want to keep. And you don't need to spin up different clusters for them. So you can secure them basically by adding users to the different projects, different feature stores, and then giving them a role. Either they can read-only role in there or read-write role. And it's not just feature stores that support this multi-tenant capabilities. We also support data sets in our file system, Hive databases, Kafka topics, and even Elastic indexes. And each of these environments, dev, prod, staging, can have their own conda environments. You can have different Python libraries inside them, and they're independent of one another. Finally, we support quite extensive support for provenance when you develop ML workflows on our platform. And we do that using the infrastructure. So we don't require people to rewrite their pipelines in frameworks like TFX or MLflow. You can just take notebooks and chain them together into pipelines. And as you save, for example, models to the file system, that gets picked up by the platform and indexed and made available through provenance. So it's not just the SaaS platform, Hopsworks AI, it's not the only way to access the platform. You can also install the community version. It's fully featured. The Databricks connector is not available in the community version, but you can get it here in Hopsworks AI or in the enterprise version. The enterprise version it extends community version with support for integration with Kubernetes, Active Directory, LDAP, OAuth 2, and GitHub support. So I'm now going to go through a demo of working with Hopsworks and Databricks. And I'm going to go through an example that's available online. You can find this code here at my repo. So it's jimdowling/churn on GitHub. It's based on a Kaggle notebook, and Feast extended that Kaggle notebook. It's a different Google Feature Store project. And the problem is basically how to predict churn of telecom users. So we'll just have a look at taking data from a table in Delta, a Delta table on S3. So this is Delta Lake. And we'll just convert it into a feature group. So we'll have a look at the feature store itself and how we make those features available. And then if we have time, we can create training data sets from that. So let's go to Hopsworks AI. So this is the Hopsworks AI platform. And what you can do here is you can register for an account. Now I've done that already, and I'm not going to show you how to do that. But what you can do is once you've registered, you'll get a dashboard and you'll get some settings. If I have actually a couple of clusters running right now, this one called Gym Databricks, and it's running in US West 2, which is the other side of the world from you right now. And we can expose or make the feature store available by clicking on these exposed services and then pressing the update button, and then Databricks can access it. So the first thing you need to do, I mentioned, is to set up the cross-account role. I've done that already. There is a tutorial you can follow for how to do it, but I can just show you briefly. It's really just 3 steps. Create the cross-account role, add an inline policy to the cross-account role, and then finally store the cross-account role ARM. So once you've done that, then when you create a cluster, that cluster will get deployed into your AWS account. Now that does mean you'll pay for the use of that cluster, but we won't charge, like I said, at least until September for the use of that. So here's how we create a cluster. We can just click on Create Cluster. I can give it a name, Databricks 42. I can pick a size of cluster. I can scale it up and down. The data for this cluster can be stored in an S3 bucket. So I have one called Gym Oregon. I stored my data in earlier. I'll just show you briefly what happens in that case. It's not this bucket, it's this one. So this is the one for the cluster I'm currently running. So you can see the data stored in these block folders here. So you can set an SSH key if you want to log into the cluster. IAM roles can be set using this instance profile. So I can pick any of the IAM roles that are available in this region. So I want an IAM role that gives me privileges for maybe to read and write to buckets in S3. And then if you deploy the cluster in the same region as the Databricks cluster, and I can see I didn't do that here, so I'm just going to go back and pick a region where we have Databricks. So we should have one in US West 2. I'll go back here. So then we have Databricks VPC. So we're able to list the available VPCs if you give us the privileges to do it. And then we'll see the Databricks VPC, and then we can select that. You will need to know, however, which subnet your Databricks cluster is located in. And I created one US West 2D. I can show you where we can see that in Databricks. So in Databricks, we have a cluster here. I'm just going to start this one. And if you go into Databricks, I'm here now in the clusters section here. And if you go down to the advanced button and you open this advanced button here, and we go down, we can see the availability zones here. So if you happen to start Hopsworks in a different one, you can always edit this cluster. So you can edit your Databricks cluster to start in a different availability zone and change that. Okay, so then once you can again connect this to an LDAP server or AD for managing accounts, and then you go ahead and create it. Now I'm not going to create it because I have a cluster already. So what I'm going to do is go to the cluster that I have running. So when the cluster gets created, it takes about 10 minutes for the cluster to be spun up. I'd already logged in earlier, so it kind of let's delete that project. We'll leave that project there for now. So I didn't need to log in, but logging in is quite straightforward. You just basically cut and paste the credentials here, so this email and password, into the boxes, and then you can log in. I ran already this tour, so if I click on the button Feature Store here, that we can see here, it will create this project here. This project is called Demo Feature Store. So there'll be a feature store in there. We can have a quick look at the feature store that's created in there. So if I click on the feature store here on the left, we can see this is the feature store. And now we have our three abstractions, the feature groups, the training data sets, and the individual features. And then there's also these storage connectors that we can define, and then the details of this feature store itself. So the storage connectors, I have two connectors to two different S3 buckets. You can create them to subpaths within buckets as well if you want. And this, if we look at this feature store as a whole, we can see that there's 27 features divided up over 7 feature groups, and I've created 5 training data sets so far. Let's have a look at the feature groups. So the feature groups in here are related to sports. So we have team features here. And if I click on one of these, clicked on the teams features one here, you can see on the right-hand side, we have details, we have tags. So I can actually define tags on these. So I can say this is anonymous data, for example, for this particular feature group. And then we'll be able to do free text search for our feature groups using these tags. So it's a great way of organizing your feature groups into catalogs and being able to search them. So as you have tens or hundreds or thousands of features, and being able to just quickly search to find them is very powerful. So these particular features, the job that was used to compute them was run on our platform, the Hopsworks platform. So what that means is that we manage the jobs to run here. Now, when we run a job from Databricks to compute a feature group, we're not going to be able to link it in because that feature engineering job happened outside of our platform. If you run the feature engineering jobs in the platform, we'll trace the provenance of them. In this particular case, I think this feature group is just offline. So we have a Hive table behind it. It's a managed table, not a hoodie table. And we can see that we can do some exploratory data analysis from in here. We can look for correlations of feature groups. We can look at descriptive statistics over feature groups. So for each here's a feature team budget, we have 5 different descriptive statistics. We have the count, number of rows, the mean, standard deviation, min, and max. And we can look at the distribution of feature values. So for the feature called team budget, this is the distribution of feature values. Okay, so this is, we have individual features. You can search through those training data sets here that were created from them. Again, we can have the same training statistics computed over them. So let's close that. So I did mention earlier that we have data validation, and I'll briefly show you the data validation support. So if I select a feature group, in this case I have team features selected, and if I click on the tick here, it says data validation. If I click on that, what I can do is I can actually now define data validation rules. So predicates, I can say, well, the number of rows of a given feature, or a given feature group, I should say, should be between 1,000 and 100,000. And I can generate an error or a warning depending on whether the number of rows is lower or greater than 1,000 or 10,000, 100,000. So these predicates, and this one has size, I could say uniqueness for a given feature. So I might say for team ID, they should of course be unique. So we want that to be between each one should be unique, and if they're not, we'll give an error. So I can basically define a lot of these rules. These are the predicates available. You can see we have ones like the mean value of a column or a feature, standard deviation, sum, entropy. This will create a job. And this job is a Spark job. It's like I said, it's a Scala Spark job earlier. It's not a PySpark job. And this can be run as part of a pipeline. So we can actually then run this after we've ingested some raw data or fact data and make sure that that data is correct before we insert it, for example, into a feature group. Now, so let's have a look at one last thing that's quite useful. Data scientists will typically want to have a quick look at the data. So you can do that by just pressing the preview button, and it'll get your data up quickly. And you can change more rows if you want more data. Okay, let's look at Databricks now. So I just started my cluster running, and it normally takes a little while for that to kick off. So it looks green is good. So it looks like this cluster is running. And what I'm going to do is, I have this one, churn create feature groups. So this notebook is available on GitHub. It's available here at jimdown/churn. It's this particular notebook, churn create feature groups. The other one called Feature Store Quick Start is quite useful. I can show that one as well. Because I'm going to spend more time on the churn create. But the quick start is a nice way of getting started. I think I ran this before. One thing that you do need to do when you start up your cluster is you do actually have to update the Spark config, right? And we have to add a script as well to our cluster. So this piece of code here, it's in the quick start, but it's also in the churn notebook. You only need to run it once for every cluster. So when you start out, you're going to import the Hops feature store, and then we're going to run this cell here, and then I'll show you how to update this. So you basically copy this Spark config data, and it says add it to the Spark config, and then save and restart the cluster. So what I did already is that here I have the cluster in front of me. I did also one other thing. I installed the Hops library. Now for the churn example, there's more libraries than the Hops library. You can see quite a few libraries here. The list of them are available in here in install pythonlibs.txt. So I installed those by hand. But the Hops one you'll need to access the feature store. So that one you should install first. And then if we go back here, what we need to do as well is that we'll need to update the Spark config. So you can see I pasted that in already. This was the output of that cell. What it's doing basically here is we're using certificates in our platform. And when you connect to the feature store with your API key, you get back a certificate that you can use to read and write to our file system, Hopsfs. So it's really just configuring that. You'll also need to go to the init script here and add this particular line, dbfs / hops scripts and init script.sh. So you just append that. And then you restart your cluster and you're ready to go. So if you keep this cluster alive, that one-time action of configuring it, it's not that much work. Right? So you'll stop your cluster, start it, stop it, and you'll have run it the once. Okay, I'm going to run this notebook, which is the Telecom Customer Churn Prediction Feature Engineering Notebook, and then I'll talk my way through it as it runs. So what we can see here is that it's going to get some data. We'll see it in a second. It's going to read up some data from this Delta table in my S3 bucket. Okay, so I'll just show you that briefly before we get started. This is the Delta table here. It's got Delta log files and then a couple of Parquet files here. If we look in our feature store, I'm actually going to write it to this demo feature store. So demo _ feature store _ Jim and a lot of zeros. So it'll appear in here as when this feature store is registered. So let me just run all the cells, and I'll talk through it as it starts running. Okay, so the first thing we're going to do is import a bunch of libraries. For Hops, we want to import the feature store. I'm not sure we actually use this one. You can skip it. And then what we do is we put in the region of our cluster, our feature store cluster, the fact that we're using the secrets manager to get this API key. And then the name of our project. This could be, production feature store development, and in fact, we're able to rerun this pipeline and point it to a different project. Like you could run this in development first, and when you're happy with it and everything's good, you can then run it against the production feature store, and it'll then create the feature group in the production feature store. This is the URL to our the public URL to our. You can see it up here to the Hopsworks Feature Store. And then we just call connect. So this connect will use the IAM role, and the IAM role for this notebook is, if we go to clusters, we can find it here. So in advanced options down here, you'll see the IAM role is right at the bottom down here. It's the instance profile. So when you start your cluster, you should select that to be the one that's able to read the secret from AWS. And the secret in AWS is available in the Secrets Manager service. I registered this one earlier. And this was the secret that I created. Okay, so this secret, the ARM fit, this is basically the API key. So I did try to create the API key token. I'll show you how to do that. When you create the API key token, you go in here to secrets, add it, and then we add it with that IAM role in Databricks that we started the Databricks cluster as. So to create the API key token, it's very easy. You just go to Hopsworks and to your user account in the top right in settings. And from here on the left, we have something called API keys. So I can create a new one. We'll call it the Databricks 2. And I want to give access to the feature store. And I want to give access also to the project because the feature store resides within a project. Maybe I'll run a job as well. So maybe from outside the cluster. So I'll add that as well. So I can copy this key, add it to the secrets key manager, say that the IAM role in Databricks is allowed to read this API key, and the details are available in the docs. And that's basically all I needed to do. Now I'm going to go back to my notebook that was running, and we'll have a look through it. Okay, so this Connect has downloaded our API key, and it's actually also downloaded a certificate that we'll use to read and write to the Hopsworks Feature Store, and that will be stored in this. This init script will set up a local directory in your mounted S3 bucket where it will store that credentials information. So this notebook, what it will do is it'll read up a data frame from this bucket in a Delta table, convert it to pandas. Let's have a quick look at what kind of data is in here. We can see there's quite a lot of features in here. It's a mix of categorical and numerical features, and we have quite a bit of data transformation going on here. So typical things you will do is you replace not a numbers with something, in this case replacing with a space. We can drop null values from total charges column because null values are not going to help. 0.15% missing data in this case. Typically, that's quite typical. Some columns will not be useful as features, so you can just drop them. And in this case, we want to separate churn and non-churn customers, so we have a column for that. And then after we've done some feature engineering, we can have a look at the data as it looks like after that feature engineering, and then we'll do some even more feature engineering. In this case, we're using scikit-learn. And the data comes out as numerical features at this point. So our categorical values are mostly gone. So the last line that's kind of the one that's important for this case is that we have a data frame at the end, and this is telecom data frame, and we're adding it to the feature store. So all we need to call at this point is feature store.create feature group, telecom, the name of the feature group, and then a description of it, and it should end up in the feature store. So what I did after that was I actually added a tag as well. So this is a new part of the API where we can add any tags that are defined. So the tags that I defined I defined one called privacy level, and tags can be defined if we go to the admin UI here, and at the bottom left-hand corner we add feature store tags. So I can add any tag I want to here. So this might be, monetary, something like that. So then that becomes an available tag that can be used to tag a feature group or a training data set in the platform. So let's have a look at the feature store now. We saw that this telecom feature succeeded, so we can see that the feature group was created, this telecom feature group here. We can see that there won't be a job because it was run outside the platform, up from Databricks. We can look at our statistics, again, as before. You can see clustering analysis, we can look at distribution values. I think a lot of these are binary features, so we have just one value or another. Maybe there's one down here which is not binary, monthly charges. Yeah, okay, so we can see distribution values for that particular feature. And the descriptive statistics is going to be quite a lot of them. Okay, so it's a slightly larger data set than one we saw before. Again, you still want to preview it. In this case, we have quite a lot of features. We have, I think, 50 or 70 features. And in some feature groups, you may have hundreds or even thousands of features. So, navigating this, you can look across. You can quickly see your data, but as you add hundreds of features, then visualizing that data is maybe less ideal. Okay, so the great thing about this with the tags now is that we can see that the tag we added, the privacy level PII, is there. And we can add arbitrary tags to organize these feature groups, but also we can add tags to training data sets in here. So if I want to organize my feature groups into development, production, and staging, for example, I have one here called staging. What I can do is this staging one I created earlier, and you can see there's less services, so we don't need to select all the services in Hopsworks. And this one is quite empty right now. Maybe I'm going to develop new features, but I'd like to also use the production feature store, because I want to develop new features here and join them with the production ones and make sure everything is good before I then migrate this feature into the production feature store. So what I did already was I shared the production feature store explicitly with this one. So that means from within this feature store, within staging, I have read access to the demo_feature store. We could consider that the production feature store. So now I can write notebooks in Databricks where I connect to my two different feature stores from the same connection, and that will be okay. And the same connection to Hopsworks. And then I'll be able to create different feature groups from the different feature stores, join them together, and create training data sets and validate that before I then migrate them to production. So if I want to search, I had PII, I think was the term I put in there. And if I search the feature store, I should find this new telecom feature group that I tagged with PII. And I think I tagged one with none, but it'll do partial matches for me as well. So it found one tag which was none here, and then anonymous is another one. So it's using actually Elasticsearch to do free text search. And this is great and very powerful. If you end up with hundreds or thousands of feature groups and training data sets and features, the ability to tag them to be able to find quickly features that have different attributes is very powerful. Okay, there are more notebooks here, but I'm running out of time, so so there's notebooks for creating training data sets here. They're in the library. Let's see if this Databricks wants to shut this for me. And I have to move up. Okay, double click on that. Okay, and this is quite a short notebook that you can run. And you can run those at your leisure. So I'm going to finish up, and I'm going to go back and present the last slide. So what we did was we looked through the Hopsworks Feature Store, and we looked at how we could use it from Databricks. And Hopsworks.ai is a SaaS version of the Hopsworks Feature Store that you can quickly use to get started as a feature store in the cloud on AWS today. If you want to find out more, you can go to our website, logicalclocks.com. You can follow us on Twitter. We are an open source project, so you can check out all the code. It's available at our Logical Clocks organization on GitHub. And you can even work ahead on the community versions and contribute. And that's it for today. Thanks for listening.